Okay. Alrighty, gang. So we made it through exam 1. You are on the other side. Today we're going to start talking about some new stuff. And there's some new homework that came out, so I just want to spend a second giving you a little overview. Before we get into the meat of it, I'll also let you know things like when the test is going to be ready and all of that stuff. So let's do those things. In order to do those things, we need to get the screen share and document camera rolling. So here they go. So, of course, this is college algebra, MAC1105, section 007. It's a lecture, and today is the 11th of February, 2021. Some announcements. First, I'm super duper proud of how well you guys handled the Zoom and honor lock proctoring stuff. I was nervous, and I had a bunch of people in the department tell me last year when I proposed this idea for the first time that it would never work. But y'all did great. The shit worked wonderfully. There was no problems. You guys all did a really good job, so super proud of that. Well done. Exam 1 will be graded within 1 week. So you'll have your grades by 11th. So next Tuesday is the 16th. It just takes a little time for me to get in there and make all the comments and things that I want to make sure everything is good. But from what I've seen so far, you guys did really good. Other sort of stuff like this, there are some homeworks opening up today. I think there are. One of them was already open. I was surprised to see that, and I had a date from last year. I must have clicked something accidentally before. But yeah, homeworks 10 and 11 are opening up today. And they're going to stay open until the 23rd, which is the start of class, not next week, but the week after, right? So kind of today and tomorrow, I'm not really counting these. I'm kind of thinking of this as next week's homework that I'm just opening a little bit early. But those guys, and also this one on polynomials. So 10, 11, and 12. I'm supposed to capitalize Tuesday. 2 Tuesdays from now. And that was the 23rd. Homeworks 10 and 11 are on power functions, and the language in there can be a little bit tricky, but if there's one section of this class where I get really finicky over the word problems, it's these guys. This is a place, when it comes to exponential functions, we'll deal with a lot of word problems, and those you guys will master. When it comes to the linear functions, we'll deal with a certain amount of word problems, and you guys got good at those. When it comes to the quadratic functions, you guys, nailed that, but it was a little bit tedious, but we got there. This section on proportionality tends to be the one where people have a really difficult time figuring out what each word means related to the algebra. In other words, like translating from the English to the algebra tends to be most challenging here, which is why it's convenient that we're having a little bit of extra time to work on these. So please don't wait until next Tuesday to look at homeworks 10 and 11. Kind of survey them today, tomorrow, over the weekend. Get a look at them and see, see if you can't start trying to think your way through the stuff. Any other announcement-y things? Nothing else is coming to mind. So today, we're going to get started on homework 10, which is on power functions with positive powers. And the related concept, which is direct proportionality. So this term, like, this thing is proportional to that thing, is something you may have heard before. Like if you're traveling at a constant speed, your distance is proportional to the time. Or that your mass is proportional to your height, these sort of things. It just means that these two things kind of grow together. And it has a very specific meaning. Mathematically, it means that one is equal to a constant times the other. A power function, on the other hand, is a function that is just your variable raised to some power. And then maybe you have a constant multiple out front. So I suppose the place to start here is with the definition. A power function is any function which can be written as f of x is some constant times x raised to some power, where c and p are constants. Right, so these are called power functions because really all they do is take your variable and raise it to some power. Maybe they multiply by a constant, but the main thing is this, right? So homework 10 is all about power functions, things like this, where the powers are positive. So p here would be a positive number. This includes a lot of functions that you've seen before, like y equals x squared, y equals the square root of x. All of those live in this land of power functions. So some examples. Y equals x is a power function. Right, the power, p here is 1. And the constant, c here is also 1. Y equals 5x squared is a power function. The power here, bullet point these, power here, p, is 2, and the constant here, c, is 5. Sometimes we'll call that constant a coefficient. And I'll explain a little bit more what the word coefficient means when we start talking about polynomials. But just know if you see the word coefficient, it means the constant that's multiplying your variable, right? So here I've got like x squared, that's my variable term, and it's being multiplied by 5. That 5 is a constant. It's certainly correct to call it a constant. But to make clear that it's the constant that's like multiplying the variable, sometimes you'll see the homework in the book and you'll hear me refer to it as a coefficient. Another example of a power function, something that's not quite as obvious, y equals the square root of x is a power function. But it doesn't look like a power function right now, does it? Can anybody help me understand how this kind of fits into this framework? Like, what is the coefficient c and what is the power p? Yeah, very good. Mark's got it. So this is, I can rewrite this as x to the power of 1/2. Right? Really, there's a 1 out front here, but I'll leave it like this. So the power p here is 1/2, and the constant, the coefficient, if you want to call it that, c here is 1. And this is kind of a neat time to say this. There's lots of other root functions besides the square root. So maybe another color here on the side. We'll say note, kind of think of this as a review of radicals. The nth root of x, this is the same as x to the 1/nth power. And the nth root of x to the m, this is the same as x to the m/n. So all of your rooting functions, not just the square root, but also the cube root, the fourth root, the fifth root, the 3/2 power function, the square root of x cubed, all of those are power functions. Now, Brooke gave an interesting response to that last question in chat, and I think it could have just been a typo, but it brings something neat up. The function 1/x², that is a power function, but that doesn't live in the homework 10 stuff. 1/x² is the same as x to the -2. And so that would be a homework 11 thing. That's really a negative power. One of the neat things about power functions with positive powers, let's look at some graphs. I'll just do a quick sketch of each of those graphs from the previous page. Y equals x, you know what that looks like. That's a line, slope 1, y-intercept 0. It looks like this. Y equals 5x². We also know what that looks like. That's a parabola. We studied those already this term. This vertex is at 0, 0. It looks like this. For example, 1, 5 is up here on this guy. -1, 5. 0, 0. Some 3 points on there. And then that last one, y equals the square root of x. This graph looks kind of like this. It goes through the point 1, 1. It kind of starts down here at 0, 0. If we wandered all the way out to 4, we would get up to 2. Right here would be 4, 2. A neat thing, if you look in quadrant 1 for each of these graphs, what is the same about all 3 of these graphs in quadrant 1? What concept that we were just tested on? Yeah, beautiful, they're all increasing. So power functions where the power is positive, they're always increasing, at least in the first quadrant. they're all increasing as long as the x values are positive and the coefficient is positive. This is kind of the idea behind direct proportionality, right? If I say that these two things are proportional, then I mean, as one gets bigger, the other gets bigger. So that is a useful observation, that in quadrant 1, these are all increasing functions. So as the input x gets bigger, the output y also gets bigger. Okay. These tend to be the main shapes for these power functions, right? If the power is bigger than 1, then the graph will kind of look like this, at least in the first quadrant. All right, outside the first quadrant over here, maybe it'll go down, maybe it'll go up. But this sort of, we call it a concave up shape, sort of like this, kind of wants to hold water, at least over here. That's typical of power functions where the power is bigger than 1. And I'll show you what I mean if we look in Desmos here. All right, so you notice if we look up here in quadrant 1, all of these power functions where the power is bigger than 1 have that same sort of shape. The red is x squared, the blue is x cubed, and the green is x to the 4. And they all kind of come in flat near the origin and then get steeper and steeper and steeper. So kind of all a little bit similar to this guy. If I look at some power functions where the power is smaller than 1, like y equals x to the 1/2. Here's that graph I drew for you a second ago, right? X to the 1/2, it's square root of x. But if I were to pick some other powers here, like y equals x to the 2/3, or y equals x to the 1/5, what the fuck? 1/5. You'll notice that in quadrant 1, they all kind of have the same shape, right? They all kind of start off vertically, like growing out of the origin, going up. And then as you go off to the right, they kind of settle down a little bit. They all do this. And the consistency between these things, what makes these things all do this, is the fact that the powers are smaller than 1. Right? The powers are positive, bigger than 0, but smaller than 1. And different things can happen over here on the left, especially with these guys. Sometimes the domain is just going to be 0 to infinity. Sometimes the domain is all real numbers. So for the purposes of college algebra, we are going to focus on what's going on in quadrant 1. We're not going to worry quite so much about what's happening over here. Okay, so these are the kind of typical shapes. We'll see something like this, we'll see something like this, or of course linear functions look like this. So this sort of quadrant 1 shape. This is typical with powers p bigger than 1. This sort of quadrant 1 shape is typical with powers between 0 and 1, right? So bigger than 0, smaller than 1. And those are two things that I would advise remembering. Of course, I don't think you need to make a special note that linear functions are straight lines, but that if the power is bigger than 1, you're going to have this like concave up shape. And if the power is smaller than 1, you're going to have this kind of like curvy concave down shape. We call this concave up and we call this concave down because of terms from calculus. If you want to see exactly where those come from, stick in the calc sequence and I'll see you in a few semesters. We'll talk all about it. Okay. This is a pretty solid introduction to the graph shapes and stuff. Let's see, let's grab a homework problem or two. I guess I should define direct proportionality, and we can grab a homework problem or two. Okay. So here's a definition. We say that y is directly proportional. Another way to say this is varies directly with, is directly proportional to x provided y is equal to some constant, I think your book uses k times x. So the thing we're defining here is directly proportional. We say that y is directly proportional to x, provided y is equal to some constant k times x. And then you'll see places where they say, you know, y is directly proportional to x to some power, x to the p. That just means this. So if y is directly proportional to x cubed, that means y is equal to some constant times x cubed. All right, so this is the first kind of definition that's going to help us understand the word problems in homeworks 10 and 11, which tend to be a little bit tricky. So make sure you put this definition somewhere you can find it, and let's take a little bit of time to understand it. I'll grab one or two of those problems from the homework, we can work them together, and then I'll let you guys go. We'll have a gentle day today, since you guys did so great on that test. So let me come in here. Where can I? Come back to this. All right, direct proportionality. Come on, see it. You can print a file. Okay, find the constant portion. Portion of x. Maybe we can do a little better. Situation varies directly as the credit. Okay. Let's look at number 2. Let's look at number 2 and we'll do it together. So I want you guys to read this along with me and then watch how I kind of interpret and translate the language into mathematics. They say, for a resident in a particular state, the total cost of tuition at the state college varies directly. Well, there's that buzzword, right? Varies with, or varies directly with. Varies directly as the number of credit hours or units a student takes. For the academic year 2006-2007, the total cost of 13 credit hours was $1,105. So the cost varies directly with the credit hours, and the cost of 13 credit hours is $1,105. So that's what we're going to start with. They said the cost, this is homework 10, number 2, bunch of bullshit. Cost varies directly as credits. And then what else do we have here? For the academic year 06-07, that really doesn't seem relevant. The cost of 13 credit hours is $1,105. So 13 credits costs $1,105. And then they want to know, how much does 15 credits cost? All right, this is legitimate stuff. Same is true here at Santa Fe, right? That we pay a certain amount for each credit. So the total cost is proportional or varies directly as the number of credits we take. You guys experience this with your tuition bills, I'm sure. So here's how you do this. You got to pick some variables. You gotta give something a name. Cost and credits both start with the letter C, so I don't want to use the letter C. But let me just call cost X. Why not? I can call cost Y, and I'll call the number of credits we take X. They said that cost varies directly as credits. And this is the same thing. Remember, this is the same thing as saying this is directly proportional. Varies with or varies as. It's just two different ways of saying the same shit. You could say varies as. It's just kind of old-timey language. All right. So the equation that I can write down is this thing is directly proportional to this thing. That means y is equal to some constant times x. That's it. There are no powers here. They didn't say the cost varies with the square of the credits or anything like that. Just straight up cost varies directly as the credits. So this is where we begin. Is everybody comfy with where this came from? Alrighty. Now they told me that if I take 13 credits, my tuition bill is going to be $1,105. Wouldn't that be nice? So 1,105 since 13 credits costs $1,105. I don't have to write dollars, I use a symbol. We know that 1105, I plugged that in for y. K is what I'm trying to figure out, and I plug in 13 for x. Once you find the constant k, you know everything there is to know about this relationship, right? The only thing we don't know here is k. X is a variable, it's the number of credits you want to take. Y is a variable, it's the amount of money that you're going to have to pay to take that many credits. So all you really got to figure out is k. What does k represent here? Before I solve for it, who can tell me what k represents in words? Very good. Yeah, exactly. It's the cost per credit hour. All right, it's the cost of one credit. If I plug in x equals 1, taking one credit, I would get y equals k times 1. So k has to be the cost of one credit hour, or the cost per credit hour. All right. From here, this is easy to solve for k, right? We divide both sides by 13. $1,105 divided by 13. Yeah, it actually is the same thing, Mark, right? So what we're saying here, when we say y is directly proportional to x, we're saying the same thing, that y is a linear function of x. The kind of interesting stuff that happens here is when we start allowing for different powers here. When I say y is directly proportional to the square root of x, or y is directly proportional to x to the 7, that's when you'll start seeing some nonlinear functions show up. But you're right that a straight up proportionality thing is the same thing as saying this is a linear function with y-intercept 0. All right, so 1105 divided by 13 is the same as 85, right? So k equals 1105 divided by 13, which is 85, which means that the cost of a single credit is $85, right? Or we're paying $85 per credit hour. Once you have the constant of proportionality k, that's the name for this constant. It's called the constant of proportionality or the constant of variation. You generally want to plug it back in here, and that will tell you the full relationship between x and y. So I'd say, therefore, y is equal to 85x. So let's return to the problem and remind ourselves what they were asking. They asked, what is the total cost of 15 credit hours? I found the cost per credit hour, which is my constant of proportionality k, and I plugged it back into my relationship here to get this. So how do I answer the last question here? What is the cost of 15 credit hours? Yeah, good. We just have to plug in 15 for x here. And off the top of my head, I'm not sure what that is, but this can help. Well, it's 1,275. So I would say the cost of 15 credit hours is $1,275. All right, this is a fairly simple example, but it's very archetypal of all these proportionality problems. You have to read the problem very carefully, trying to pick out the important parts, right? You'll notice that's what I did here. I certainly didn't write down the whole thing. I just looked at the problem for the information that I thought would be useful. One of the things that will be useful in all of these is, what is the proportionality relation, right? Who varies with whom, or what varies with what? Then the other thing you're going to need is some amount of specific data, right? Like one particular value for this thing and one particular value for this thing that you know are linked to each other. That's the necessary information to find the constant of proportionality, k. And then generally these problems will ask you to do something else. So they'll tell you the proportionality relationship. They'll tell you one particular piece of data, like one value for one variable that corresponds to a value for the other variable, which will let you solve for k. And then they'll ask you to do something with this relationship once you've solved for k. So here, this was our proportionality relationship. Cost varies directly with credits. This was our specific bit of data that let us solve for the constant of proportionality. 13 credits cost $1,105. We solved for that constant of proportionality. We got 85. We updated our equation. Now with that new updated equation, we could do whatever we want. So we go back and we look at the last part of the question. We ask, okay, what is it they really wanted us to do with this? How much does 15 credits cost? Well, now that I know the exact relationship between credits and price, I can just plug in the number of credits. You want to know what 15 credits cost? I plug in 15 for X. You want to know how many credits do I have to take to spend a $2,000 tuition budget? I would plug in 2,000 for Y and solve for X. You want to know how much does 5 credits cost? You plug in 5 for X. A surprising number of things in the real world are proportional. You can get shockingly far just by assuming two things that grow together are proportional. The best example of this is F equals ma, right? This is Newton's big discovery, that force is equal to mass times acceleration. In other words, force is proportional to acceleration. All right, how are we doing on time here? It's 10:07. I promised to let you guys go a little bit early today. I want to look at least one slightly more challenging problem, and then I will let you guys go. Again, before we get to a place where everybody's starting to sign off, I want to remind you that homeworks 10 and 11 tend to be a little bit challenging. There's lots of word problems, and you have to very carefully interpret the language. So please take the time to read these. This is going to be open all next week. And we will talk more about them, but I just want to introduce these and get you guys thinking. So, this is positive. Yeah, we'll get to that. Yeah, this is a good one. I'm going to look at number 14. Actually, I'm going to modify this slightly. We'll look at a bit gentler one. But a neat fact the area of a circle is directly proportional to the square of its radius. A circle of radius 2 has area 4 pi. Two things. Find the exact formula for the area of a circle. And then part B here, we're going to say if the radius of a circle doubles, what happens to its area? Okay. Now, I know most of you know the formula for the area of a circle, and I'm not trying to insult you by giving you a problem where we kind of pretend like you don't. The idea here is to discover that formula from the information that's given, and to recognize it as the thing that we knew before. If we didn't know it before, that's fine, no harm. The important information that we should sort of pick out here is that area is directly proportional to the square of the radius. So let me call the area A, and I'll call the radius R. What equation can I write down based on the underlined bits there? Well, this is directly proportional. So I can start with A equals K times what? What is the area directly proportional to? Is it directly proportional to R? You guys still with me here?
R squared?
Yeah, exactly. Directly proportional to r squared, right? The square of the radius. So A is equal to some constant k times r squared. Okay. Now, they tell me that a circle of radius 2 has area 4 pi. So when r is equal to 2, A is equal to 4 pi. So we can plug these things in. I know that 4 pi is equal to k times 2 squared. All right. When r is equal to 2, A is equal to 4 pi. B says, if the radius of the circle doubles, what happens to its area? Yeah, we'll get there. So for now, let's continue on part A. We still got to finish part A. I know that 4 pi is equal to k times 2 squared. Well, 2 squared is 4. And now if I divide both sides by 4, I get that pi is equal to k. So the constant of proportionality here, and I'm sure everybody knew this, is pi. So the area formula for a circle is A equals pi times r squared. This is the end of part A. All right, so this is the solution for A. The solution for B is a little bit more complicated. And Mark nailed it in chat, which is awesome. But I want to walk through it kind of gently. First, are there any questions about part A here? Okay. Part B is nifty. So we say, if the radius of a circle doubles, what happens to its area? So here's the solution for part B. We know that the formula for the area of a circle is A equals pi times r squared. We want to know what happens to the area when the radius doubles. And it can be fun to think about this in terms of a picture. Here I have a circle of radius r. If I double that radius, how much bigger a circle do I get? I'll approximate here. What is this? This is like 1/10 thickness, like 2 pen thicknesses. Is that about 2r? Yeah, about like that. Would be about 2r. So here's my center. Circles are hard to draw, but I think we would all agree that the area here is definitely more than double the area here, right? In fact, you could take one of these little circles and slide it in right here. And you could take another one and slide it in right here. And you'd still have all this space over here and all this space over here left over. So what happens to the area when the radius doubles? Mark said that this should quadruple. How would we show that? What does it mean to say the radius is doubling? If we start with a circle of radius r, then doubling that radius gives us a circle of radius 2r. So the area for a circle of radius r is pi r squared. The area for a circle of radius 2r should be pi times 2r squared. Well, that's the same as pi times 2r times 2r, which is the same as pi times 2 times 2 times r, which is pi times 4 times r squared. Or 4 times pi r squared. So if you compare this and you compare this, yeah, this guy is 4 times bigger than this guy, right? That's this 4. So indeed, the area quadruples. The area goes up by a factor of 4. All right, and that's the language we would say. Quadruples is really good. You could say that, or you could say it goes up by a factor of 4, it gets multiplied by 4. These tend to be the parts that folks struggle with the most. So I want to take a second and answer any questions that we have here. I know that this can be a little bit weird and counterintuitive. Okay, one last little thing in parting here, and that is some rules for exponents, right? You notice here I actually wrote 2r squared as 2r times 2r and then shuffled things around. You don't want to always have to do this. This can be pretty tedious. So the last thing I'll leave you with here are some very, very important rules for exponents. You must master these. They'll make this section easier, and when we get to exponential functions, you will absolutely need them. When we talk about logarithms, which is going to happen sooner than you think, we will be coming up with new versions of these, so you really, really, really need to get comfy with these. if you multiply two numbers together and raise that whole thing to some power, that's the same as a to that power times b to that power. This comes from the fact that multiplication is commutative. If you have a to some power and you multiply that by a to some other power, right? So the bases are the same, but the powers are different and you want to multiply those. That's the same as a raised to the sum of those powers. Similarly, if you divide terms with the same base, that's the same as subtracting the powers. All right, these are the main rules that I need you guys to know. But I'm going to add here a couple little things. Raising something to a negative power is the same as taking the reciprocal of that thing to the positive version of that power. All right. And then we mentioned this one earlier, the nth root of anything is that thing raised to the 1 over nth power. Right. So these are the rules for exponents that you guys need to be comfortable with. I'm sure you've seen these somewhere else in high school or maybe in an earlier class. These first few are going to be very useful. So pay extra careful attention to these guys. These guys we're going to use a lot also, but they won't be quite as pervasive as these. Alrighty, this is where I will let you guys go for today. You all did wonderful on that test on Tuesday. I'm very proud of you, very proud of how well everybody did with the proctoring system and the results on the exam itself. I will finish grading those no later than next Tuesday. So next time we see each other, you should have your exam 1 grades. If you have any questions, feel free to send me a Canvas message. Otherwise, I will see y'all later. Any burning questions or issues you want to discuss before I let you go? Okay, have a good afternoon, everybody. Over the weekend, please do look at homeworks 10 and 11. They tend to be tricky. And I'll see you on Tuesday of next week.
Thank you.